So let us see the statement. So P be a prime number and let A be a number such that A is not congruent to 0 mod P. So that is P does not divide A. Then the numbers A, 2A, 3 up to P minus 1A are same as 1, 2, 3 up to P minus 1 in modulo P in some different ordering. Right?
Let's see, I remember that 1A, 2A, 3A, and so on, and then we said that those are the same numbers as below, except that
Right.
they are in different order.
Okay. So they are as a list. They are same numbers. In some maybe the ordering may be different. Right.
Right.
Right. So this lemma will be used to prove the Fermat's little theorem. So that statement we ended in the last thing. So let us recall see the statement. So the statement of the Fermat's little theorem, it says that P be a prime number and let A be any number such that same condition P does not divide it. Then this thing holds, that is A power P minus 1, that will be congruent to 1 mod P.
Let's see. Let P be a prime number and let A be any number such that A is different than 0. A is not equivalent to 0.
Yes.
Mod P. Then A P minus 1. Okay.
Okay. So let us try to prove that. Okay. So let us try to prove this theorem. So the thing is, we will use that lemma that we saw just now to prove the theorem. So using the lemma, what I have, so then the list of numbers, that is A to A up to P minus 1A modulo P and 1, 2, 3 up to P minus 1 modulo P. So these are the same, right? As a list of numbers are same.
Mm-hmm.
Right. So then the product of these numbers will be equal to the product of the second list of numbers, right?
The product of which ones?
The product of all these numbers will be same as the product of all of these numbers, right?
Right, yes.
Right. So the product of the numbers in the first list is equal to the product of the numbers in the second list. So this implies, so A times 2A times 3A up to P minus 1A. So that is congruent to 1, 2, 3 up to P minus 1 in modulo P. Right?
Mm-hmm.
Okay.
Right.
So now what you can do is, so here you can see that each of the term contains A, right? So each of the term
Right.
has A. So how many A's are there?
How many A's there are going to be? P minus 1 A's.
Right. So you can separate out A to the power P minus 1, right?
Right.
And what is the remaining term?
1, 2, 3 factorial. Oh
Right.
no.
So p minus 1 factorial, right?
P minus 1 factorial, right? Yeah.
Right. On the right hand side also I have p minus 1 factorial modulo p. Yes. Now the thing is, so we know that there's p minus 1 factorial, so it is relatively prime to p, right?
How do we know that is relative prime to p?
Yes. So what is p minus 1 factorial? So it contains all the terms up to 1 to up to p minus 1, right? So p does not
Oh,
divide
okay.
any of them, right?
Right.
Relatively prime to p. So we can cancel them from the both side. So this implies one more p, right? So this is what we wanted to prove, right? So this is the statement, right? This is what we wanted to prove, right?
Okay, so what is the lemma again? So the lemma is if p is a prime number,
Yes,
and
p is
a
a prime
is
number.
a
Yes,
number such that a is not equivalent to 0 mod p.
right. Then these two set of as a list of numbers, these two things are same. Maybe their ordering is different. That is a lemma, right?
Okay.
Okay.
We prove the lemma right now.
Yes. No. We proved the theorem, right?
That's
Lemma
the
we proved.
theorem.
Yes.
We use the lemma in which a to a 3a is the same as 1 to 3.
Yes. Yes. That is the why we use the lemma.
Okay.
Right.
Mm-hmm.
Yes. So let us see some application of this Farmer's Little theorem. So from this, I know that if the p has to be prime, so that is the condition required. So let us see some application. So the Fermat's little theorem. So can be used to show that a number is not a prime. Actually, without factoring it, because to check factorization it is very difficult without actually factorizing it. So this is one application. So we can check whether the number is prime or not without factorizing it. So for example, if I take 2 power 1, 2, 3, 4, 5, and 6, 6. So this is my number. Sorry, this 6, 7. This is actually congruent to 8, 9, 9, 5, 5, 7 in modulo 1, 2, 3, 4, 5, 6, 7. So the thing is, the number I have taken here is, so this is my number. So, and here you can say, check that this is nothing but n minus 1, right? So if n was prime, then this quantity should have been 1, right? Because if n was some prime p, then by the Fermat's little theorem, I know that 2 power p minus 1 is congruent to 1, right?
Mm-hmm.
But here it is not equals to 1, right? So from here we can conclude that this number is cannot be prime.
So you're saying we want to prove that 2 to the power of 1 to 3 is not a prime.
No. You suppose this number is given to you, or 1, 2, 3, 4, 5, 6, 7. So this is the number. and you want to check whether it is a prime or not, right?
Uh-huh.
Yes, but getting prime factorization for a large number, it is difficult, right? So
Okay.
here we are using the Fermat's little theorem because of that. So the thing is, so if at a is 2 to the power n minus 1, so n is our number. And then we see that that is congruent to this 89957 modulo n, right? But that is not equals to 1, right? Because if it was a prime by Fermat's little theorem, it should be congruent to 1, right?
Wait. So where the number 899,557 comes from?
No. This I am just writing. So this also you have to calculate, but I am just showing you the application of pharmaceutical theorem. So this number, yes, that is done. So suppose you know this congruence. That is what we are doing. So the thing
Okay.
is that this information is given to you. So this for now we are not seeing how to get this number. So suppose this information
Okay.
is given to you, and we want to check that this number n whether it is prime or not, right?
Okay.
Yes. So now we what we get? So this is number n, and we get that 2 power n minus 1 is congruent to this number modulo n, but that is not congruent to 1, right?
It's not congruent to 1, okay.
Right. But if it was prime, it should be congruent to 1 mod n, right? By the Fermat's little theorem.
Which one should be congruent to?
This whole quantity. Okay, let me write down. That will be easier. So it cannot be prime, since if it were, then the pharmaceutical theorem I will write at FLT. Okay, then it will be easier. So then FLT would tell us that this 2 power 1, 2, 3, 4, 5, 6, 6. So that must be congruent to 1 modulo this number, right?
Mm-hmm.
Right, but that is not true, right? By the pharmaceutical theorem, if this number was a prime, this condition should hold, right? Because 2 is not divisor of this thing. So a I am choosing 2. I can choose my a as 2, and p is this number is p, and this number is my p minus 1. So by pharmaceutical theorem, I have a power p minus 1 is congruent to 1 mod p, right?
Mm-hmm.
Yes, but that is not matching with the given condition, right? So this is given to me. So these two things are not equal. So hence, this number n cannot be prime.
You're saying it is not prime because when we replace p and p minus 1, we can say that 2 to p minus 1 equivalent to 1 mod p does not hold true because above we have something different.
Yes. That is what it is.
Okay.
Right. So that is the idea. So we can also, so without factoring, we can check that whether a given number is a prime or not, right? So in fact, so this number actually has a factorization, but still it is big number. So this 1 to up to 7. So this I can write as 127 times 9721. So it has a factorization, but it is difficult, right?
Right.
Right. So I think this is more or less the content of the chapter. So let us see the exercise problems. Okay.
But wait, so here only the conclusion will be since 2 to the power of p minus 1 is not equivalent to 1
Right.
mod p, then we say that p is not a prime number.
Right. So we can conclude that P is not a prime number.
Okay. Okay.
Right?
Mm-hmm.
Okay. So next, let us say this. Okay. So the first one is, so they are saying use Fermat's theorem to perform the following task. Okay. So find a number that is between 0 and 73, strictly less than 73, with a power of, so a is congruent to 9 power of 794 in modulo 73. So basically, we have to find 9 power 794 in modulo 73. So what is the value?
We need to find, sorry?
Yes, we want to find the value of this modulo. This 9 power 794 to in mod 73, what is the value? So that is a. What is the a they want to find out? Right. So here you have to use the Fermat's little theorem. So yes. So try how to use it.
Okay, we can replace P and P1, so P will be 73.
Yes. So 73 is a prime number. So
If
9 we can.
P1,
Yes.
mhm.
So a is 9 and p is 73. So in our Fermat's little theorem. So then what does it give?
How come A is 9?
Because here our problem we have 9 power something, right? So we have to replace a by 9, right? So that a and p will change according to the problem, right? So that is the theorem statement. It says that it works for any a that is not congruent to 0 mod p, right? So here 9 and 73 they are not divisible. So yes, that we can do, right?
I mean, how do you know A is 9? Because A could be an other value between 0 and 72.
Oh, sorry. Okay, this a and this a is confusion, right? Yes. I'm talking about a in the statement of the Herman's little theorem. So yes, there is a confusion. Yes. So yes, that statement of the Herman's little theorem, we have an a, right? I was talking about that a. Yes, I was telling about this a.
Yeah, but how do you know that A is 9?
Yes, that so from the statement, the a is 9 because we have 9 power something, right? So we have to apply on 9, right? This a is different, yes. So just you tell me by Farmer's little theorem what I have. So P is 73. So what does the Farmer's little theorem say? So it says that 9 power 73 minus 1. So that is congruent to 1 mod 73, right? So this is by Farmer's little theorem, right?
Okay, yes.
So now is it clear, right?
Okay, you're choosing 9 because it is helpful.
Yes, because the problem it's 9 power something I have to show, right? So that's why you have to choose 9.
Okay.
Okay. So this simplifies to that 9 power 72. Yes. Now what to do? How should I get to that power 794?
You can multiply maybe, right?
Multiply by?
If you multiply by 9 to the 794 on both sides.
Okay. So if I do, then it will be. So if I multiply with this quantity on both sides, so then it will be 72 plus 794 here, right? But how
Right.
will that help? Means how will you able to find that?
I mean, mm, If we just multiply both sides by 794 minus 72.
Yes, then also we have yes. So 794 minus 72 you are trying to say. So then also it will be some quantity, right? So then we have to find that quantity, right? So that will reduce to the same problem, right? Same idea, right? Yes, eventually that we have to do, but the thing is we can do it in a single step. So let me tell you. So the thing is, what I know is 794. We can apply the division algorithm to find the quotient and remainder when we divide by 72, right? So tell me, what will be the quotient and remainder when I divide by 72?
By 72, let's see. Eleven is the Q.
Right, 11 is the quotient, and what is the remainder? So 11 times 72 plus
2.
2, right? So this is the thing. Okay, so now we can start with this on the 794. So this is nothing but now I can write it as 11 times 72 plus 2, right?
Mm-hmm.
So this is 11 times 72 times 9 square, right? Okay,
Mm-hmm.
right. So now this what I can write is 9 power 72, then whole power 11, right? So that is what is the term, right?
Okay.
Right. But I know that 9 power 72 is 1 mod 73. So now when I take modulo, so it becomes 1. The first part becomes 1 and I am left with only 9 square in modulo 73. Right?
Right.
Right. So now it is easy to calculate. So it is just 81 modulo 73 and that you can just calculate. So I think that is 8, right? So it is 8 mod 73. So your answer, that A number that you are asked to find out, that A is 73.
You're saying you are eliminating 9 to the 72 because it is 1.
Right. So that we know already using the Fermat theorem, right?
So we start at 9 to the 724, and then we separate that into 72 to erase the. Okay, you use order the Fermat theorem. So you start from the 9 to the 794, and then from there you get to the Fermat to the EFLT.
Right.
Okay, I see.
So this is fine, right?
Mm-hmm.
Okay. So I think the next part you can do, I think. So the part B, what they're saying is.
X to the 86.
Right. X power 86 is congruent to 6 mod 29. So here you have to find X.
Yeah, but here the same thing. Like, what would be A?
Yes, yes. So here A exactly we don't know, but A we can choose X, right?
Which one?
Because yes, tell.
We can choose which one?
X we can choose, right? Because X power something is there, right? So that is what fitting into that problem, right?
So X to the 28 will be
Yes,
equivalent
yes.
to
But
1
before
mod
that we have
29.
to yes, but before that we have to make we have to write one line that x is not congruent to 0 mod 29, because that is also one condition we have to check, right? Because x, there is a variable, right?
X,
So,
sorry.
so x is a variable, right? Here, x you have to find, right? So we
Right.
have to make sure that x is not congruent to 0 mod 29. Then only we can apply the Fermat's little theorem, right?
Okay.
Right. So that is easy, because so if x is congruent to 0 mod 29, so that will imply that x power 86 is also congruent to 0 mod 29, right?
Mm-hmm.
But that is not true, right? Because it is given that it is congruent to 6 mod 29. So therefore we can assume that x is not congruent to 0 mod 29, right?
You're saying if x is equivalent to zero, then
We can raise to any power, right? So that will be still 0.
okay.
Fine.
Mm-hmm.
Right. So safely we can assume that x is not congruent to 0 mod 29. So now we can apply the Fermat's theorem. So what I have, so x power 28 is congruent to 1 mod 29. Guess now how to proceed.
I mean, you can do the same thing as before. You can split those 86 into
Yes.
28 plus something.
So 86 is how many times it will go?
Oh, let's see. 3.
Right. So 3 times 28. I think remainder is 2, right?
3 times. Yeah.
Okay. So then what I can do is we can start with x power 86. So this I can write as x power 3 times 28 plus 2. So we can separate. So x power 28 whole cube times x square, right?
Yes. Then we simplify, right?
But this is x square in modulo 29, right? Because x power 28 is 1.
Yeah.
Okay. So what we have is, so x square, that is congruent to 6 mod 29, right?
Mm-hmm.
So x square is 6 mod 29. Right. Now it is easy. So now 29 means we have only have to check from 0 to 28, right? So that we can now manually check and find the values of x, right?
Repeat that last part.
Yes. So what I'm saying is now the power is significantly reduced, right? So we have to only x square is there on the left hand side, right? So now we can manually check for all the values. 29 is a small number, right? So it is from 0, 1 to up to 28. We can all put the values one by one and check.
So that restriction above. Oh no, that was for number. That was for A. No, never mind. So yeah, so x would be from 0 to 28.
Yes, yes. So yes. So now how to yes. Now we have to we can see manually which ones is working, right?
We are just gonna like test it all.
Yes, yes, we have to manually check. So that is the only way of till now.
Okay, let's see. I mean,
Yes. So for example, one. Okay, let me write down. So it will be easier. So zero will not work. That is of course. So one is also not working because one square is one. Two, three is nine. That will also not work. So like that, I think five up to five it will not work. But if I choose, so these things will not work. So if I choose x equals to 6, then x square is 36. So that is your 7 mod 1 29, right?
hmm?
So this is 7, right? 7 mod 29, right? Fine.
Yeah.
Okay, so next, if I put x equals to 7, then what happens? So it is 49 and it is congruent to how much in modulo 29?
That would be zero, no? Zero, right?
No, 29. Modulo 29. How much will be? Not 0, right?
Oh, 49, 29, 20.
Yes, 20. And if I put x equals to 8, then it is 64. 64, I think it will go 2 times.
25.
Yes, so it is 6 mod 29. Right. So x equals to 8, one solution we got, right? Right. Okay.
Yep.
Yes. So one. So actually, we can reduce our calculation also significantly because so since we are trying to solve x square, right? Also we know that suppose any mod. So here example modulo 29 we are taking. So 0, 1, 2 up to. So last few numbers are 26, 27, 28, right? So these are the whole set, modulo set. But this number I can write it as minus 1, right? In modulo 29. Twenty-eight I can write as minus 1, right? Similarly, 27 I can write as minus 2 in modulo 29, right?
27.
I can write it as minus 2, negative 2 in modulo 29, right?
Minus 2, right? In
Yes.
negative, yep.
Right. So similarly, I can go on. So this is minus 3. So I can go up to middle one. So middle one I think is 15. So the thing is, if I check up to 15, then it is done. Because when I do x square, if 1 does not work, minus 1 will also not work, right? Because after taking square, it is both the same.
Mm-hmm.
Right? If 2 does not work, then minus 2 will also not work. Because 2 square is 4, minus 2 square is 4. So both are not working. So if I check up to 15, we are done. Right?
Mm-hmm.
So is this argument clear?
Let's see.
Is anything, any conclusion?
Mm-hmm.
No, no. Any doubt you have? Or is it clear?
So the very end, the only thing that is left is to try from 0 to, well, not 0, I guess, from 1 to 28 to find out which one is equivalent to 6.
Yes, yes. But the thing is, after that, what I told is you don't have to check all of them. So half of them, if you check, then you are done, right?
Mm-hmm.
Because it is symmetric. So if it so 1 and 28 both are symmetric, right? So because 28 I can write as -1. So since we are doing x square, so if 1 does not work, -1 will also not work, right? So that's why we don't have to check through all the numbers. So we can check half of the numbers, then we are done. Okay.
Mm-hmm. Yep.
Right. So since 8 is working, so -8 will also work, right? So if I take x equals to -8, then x square is still 64, and that is 6 mod 29, right? But what is -8? But -8 is nothing but in mod 29 it is 21, right? So x equals to 21 will be another solution.
Hello?
Yes, is it fine?
Mm, mm-hmm.
So 21 x equals to 21 is also another solution, right?
21. Yeah, I mean, it is because it's like the inverse of the module or something like that.
Yes, it is
29.
symmetric about the middle object, right? Because 8 will work, -8 will also work, because we are looking at a quadratic congruence, right? X square.
Okay, the symmetry.
Yes. So yes, remaining I think you can check. So remaining I think will not work. So this thing has only two solutions. One is 8 and one is 21 in modulo 29. So I think that
Mm-hmm.
is what they wanted to find out. So solve for x. So there are two solutions. One is so this congruence. So x power 86 is congruent to 6 mod 29. Has two solutions.
Mm-hmm.
So x is congruent to 8 mod 29. It will work. And x is congruent to 21 mod 29. So these two are the solution set. Okay. So this is fine, right?
Mm-hmm.
Right. Let us go to part C. So part C they are saying. So solve x power 89, which is congruent to 3 mod 30. Yes. How to solve this one? Sorry, that is 39, not 89. X power 39 is congruent to 3 mod 30. So if we apply the Fermat theorem, how it will happen? So we can apply the similarly the Fermat-Slade theorem, right?
Let's see. Mm, I mean, we do the same thing, right? We split
Yes, yes.
13
So
to the power something.
yes, so using the Fermat-Slade theorem, so what I have is x power 12 is congruent to 1 mod 13, right?
Mm-hmm.
Right. So now 39 is how much times it will
12.
go?
Uh, it's, 3 times.
Right. So 36 plus 3, right? So x power 39, so it is x power 12 whole cube times x cube, right?
Yep.
So that will boil down to x cube modulo 30, right?
Right.
So eventually we have to solve for x cube is congruent to 3 mod 13, right?
Mm-hmm. Yep.
So yes. So the thing is what? So now same thing. We have to check for 0, 1 up to 12. So which one will work, right? So yes.
But there should be any number uh, which cube is greater than 13.
Yes, yes. That will automatically come, right? Because if we go some numbers, then it will automatically cross 13. So for example, so for 0 will not work. 1 is 1 cube, that will not work. 2 is your 8. 2 cube is 8. 3 cube is 27. So what is the modulo thing? So 3 cube is 27. So this part will not work.
27, 1.
Yes, 13 is mod. That is correct. Then 4 cube 64, right? That is I think congruent to how much?
64, 4, 4, 12. I think it starts.
So that's 12, right? 64 is 12 mod 13, right?
Mm-hmm. Yeah.
Yes. So I think similarly you can check up to 12. So the thing is you can check that none of them will work. So
None of them.
none of them is 3 mod 13. So that you can I think verify. So this has no solution.
And you cannot know in advance that.
Yes, still.
I'm saying you cannot know that in advance.
No, no. So yes, that this is not very much calculation because only 12 numbers out of which you know 0, 1, 2, 3 this will not work. So from 4 to 12 we have to check that cubing all of them. It is none of them is actually equals to 3 mod 13,
Okay.
right?
All right. So you test all the numbers and you find out that there is no solution for that.
Right, right.
And okay.
Okay, I think that is fine. So the next one is so the quantity p minus 1 modulo p. So that appeared in our proof of the Fermat-Slade theorem. So we do not know the value, right? Because so we just use the fact that p minus 1 factorial is not 0 mod p, right? That is they are co-prime. So that is the fact we have only used. So so here actually they are asking. So compute p minus 1 factorial modulo p for some small values of p. And try to find a pattern. So that is the question. Okay.
Okay.
So yes. So let us check for some small values. So p is 3, suppose. Then what is p minus 1 factorial?
2
factorial, right?
2
So 2 factorial is 2. So that is also 2 in modulo 3, right?
Right.
Okay. So now let us check what happens if p is 5. Then I have 4 factorial, right?
4
So 4 factorial is how much?
24.
24, yes. In modulo 5 is how much? 4, right?
So you're saying, okay, 24 modulo 4, okay, modulo 5, okay. 4.
Right.
Right.
So p is 7. Then 7 factorial is how much?
That would be 5040
Yes. So with modulo
with
504.
module 6.
No, modulo 7.
Module 6, right?
No, modulo 7, right? Modulo p.
But if P is 7, then the factorial would be 6.
Yes. 1 minute. So, okay, sorry. So this is, yes, 6 factorial, yes.
720.
Yes, 720 in modulo 7. That is 6 again, right?
6.
Yes. So one pattern what you can see is, so p minus 1 factorial is nothing but p minus 1 in modulo p, right? So that is what you can guess. So that is congruent to p minus 1 modulo p, right? So this is the,
Oh, I see.
right. So this is means at least from these 3 conditions, that is what we can guess, right?
Right.
Yes. So yes, so that is the conjecture, or what is they are saying, that find a pattern and make a conjecture. So that is the conjecture, right? So actually, this is called the Wilson's theorem. So there is one more theorem. So this is actually a theorem. So this is called the Wilson's theorem.
Okay, interesting.
So up to this is clear, right?
Yeah.
Yes.
Yeah, only the part where you said that we can use a little Fermat theorem to find out whether a number is prime or not.
Yes. So that yes, that will actually, yes, that is the converse part, right? So if the Fermat's little theorem statement says that a power p minus 1 is congruent to 1 mod p, that will be true for any a which is not congruent to 0 mod p, right? So we can say the converse, right? If p, if suppose I have some number such that this part is not equals to 1, so then that number is not a prime, right?
When you say that number, you mean p?
PB, yes. P is then not a prime, right? Because then otherwise, then the Fermat theorem will be contradiction, right? It is contradiction to the Fermat theorem.
Right. Okay.
Yes. Okay.
Yeah.
Okay, so the proof of the Wilson's theorem we'll see in the next class because it will take some time.